Hi all, welcome to new class. Today's class is about power factor improvement. So, what is power factor? So, power factor is the cosine of angle between voltage and current in an AC circuit. So, power factor is the cosine of angle between voltage and current in an AC circuit. That is, it is represented as cos phi. Power factor is cos phi, and the AC circuit may be inductive or capacitive. So what is inductive AC circuit? If the current lags behind the voltage and the power factor is referred to as lagging. That is, power factor is lagging, is called inductive circuit. So in an inductive circuit, the current lags behind the voltage and the power factor is lagging. Whereas in capacitive circuit, the current leads the voltage and the power factor is leading. Consider an inductive circuit taking a lagging current I from the supply voltage V. The angle of lag being phi. Then this is the phasor diagram, and the circuit current I can be resolved into two perpendicular components, that is I cos phi and I sin phi. I cos phi is in phase with the voltage V and I sin phi is out of phase, that is 90-degree out of phase with the voltage V. And here I cos phi is known as the active or wattful component, and I sin phi is called the reactive or wattless component. And here the reactive component is a measure of the power factor. If the reactive component is small, then phase angle phi is small and hence power factor cos phi will be high. Therefore, a circuit having small reactive component will have high power factor and vice versa. Next is power triangle. So, if in the current triangle, that is, this is the current triangle, that is I cos phi, I sin phi, I are the sides of this current triangle. So if each side of the current triangle are multiplied by the voltage V, then we get the power triangle. So this is the power triangle, and here Vi cos phi, that is OA, Vi cos phi is the active power in watts or kilowatts, and AB is Vi sin phi, which is the reactive power in VAR, that is volt ampere reactive or kVAR, and OB is called V into I, that is apparent power in volt ampere or kVA, that is kilovolt ampere. And in this power triangle, if we apply the Pythagoras theorem, that is OA whole square plus AB the whole square equal to OB the whole square. It is Pythagoras theorem. Base square plus altitude square equal to hypotenuse square. So here OA is Vi cos phi, that is Vi cos phi the whole square plus AB is Vi sin phi the whole square equal to OB is V into I all square. That is Vi cos phi is in kilowatt, or this is the active power. So we can write active power whole square plus reactive power whole square equal to apparent power square. That is, active power is in kilowatt, that is kilowatt square, plus reactive power is in kVAR whole square equal to apparent power is in is kVA whole square, that is kilowatt square plus kVAR square equal to kVA the whole square. Or from this power triangle we can write the power factor, that is cos phi is equal to, what is cos phi? OA, that is adjacent side divided by hypotenuse OB, and that is VI cos phi divided by VI, or in units we can write kilowatt divided by kVA, and that is VI cos phi is the active power and kVA is the apparent power. So power factor is equal to active power divided by apparent power. So the power factor of a circuit can be defined in three ways. That is, power factor is equal to cos phi, that is the cosine of the angle between the voltage and current. Then power factor is also equal to R by Z, that is the ratio of resistance and impedance. Then power factor is also equal to ratio of the active power and apparent power, that is kW divided by kVA. Next is disadvantages of low power factor. So power factor plays an important role in an AC circuit because the power consumed depends upon this factor. That is, power is equal to VL IL cos phi. And from this we can write IL is equal to P divided by VL cos phi. And this is the case for single phase, and if it is three phase supply, then we can write P is equal to root 3 VL IL cos phi, and here also IL is equal to P divided by root 3 VL into cos phi. So this is for single phase and this is for three phase. So here for a fixed power and voltage, the load current is inversely proportional to the power factor. That is, IL is inversely proportional to cos phi. So lower the power factor, higher is the load current and vice versa. So a power factor less than unity result in certain disadvantages. And let us check what are the disadvantages of low power factor. So first one is large kVA rating of equipment. That is, we have kVA is equal to kW divided by cos phi. So here kVA is inversely proportional to cos phi, that is the power factor. So smaller the power factor, larger is the kVA rating. So at low power factor, kVA rating of the equipment has to be made more. So making the equipment larger and expensive. Then second disadvantage is greater conductor size. To transmit or distribute a fixed amount of power at constant voltage, the conductor will have to carry more current at low power factor. That is, from this equation, we know that if the power factor is low, then the load current will be large. So to transmit or distribute a fixed amount of power at constant voltage, the conductor will have to carry more current at low power factor, and this necessitates large conductor size. Next is large copper loss. So, if the power factor is low, the load current will be more. Hence, the large current causes more copper losses. That is, I square R losses will be more due to the large current. And this will lead to poor efficiency. Then fourth one is poor voltage regulation. The large current at the low power factor causes greater voltage drops in alternators, transformers, then transmission lines and distributors, and this result in the decreased voltage available at the supply end, thus impairing the performance of the utilization devices. So, in order to keep the receiving end voltage within the permissible limits, extra equipment is required. That is, voltage regulators are required. Then, next one is reduced handling capacity of system. So, the lagging power factor reduces the handling capacity of all the elements of the system. It is because the reactive component of the current prevents the full utilization of the installed capacity. Then, what will be the causes of low power factor? So, most of the AC motors are of induction type and which have low lagging power factor. So, this is one of the reason for the low power factor. Then, next is arc lamps, electric discharge lamps and industrial heating furnaces operate at a low lagging power factor. Then third one is the load on the power system is varying. That is, it will be high during the morning and evening and low at other times. So due to this, during the low load period, the supply voltage is increased and which increases the magnetization current and which leads to the decreased power factor. So these are the main causes of the low power factor. So, and these are the disadvantages of the low power factor. So we have to improve the power factor. So next we will discuss about the power factor improvement. So how can be the power factor improved? So next is power factor improvement. That is how we can improve the power factor. So the low power factor is mainly due to the fact that most of the power loads are inductive, and so most of the power loads are inductive and therefore take lagging currents. So in order to improve the power factor, some device taking the leading power factor should be connected in parallel with the load. So one of such devices can be a capacitor. That is, if we connect capacitor in parallel with the inductive loads, then we can improve the power factor. So, the capacitor draws a leading current and partly or completely neutralizes the lagging reactive component of the load current, and this raises the power factor of the load. So, let us illustrate the power factor improvement by a capacitor. So, consider a single phase load taking a lagging current I at a power factor cos phi 1. So the capacitor C is connected in parallel with the load. Then the capacitor draws a current IC, and which leads the supply voltage by 90 degree. So we can draw IC here. So IC leads the supply voltage by 90 degree. Then if we connect the capacitor, then its current is leading the supply voltage by 90 degree. Then the resulting current I dash, that is, this is the resulting current I dash. So what will be I dash? It will be the phasor sum of this IC and I. So we can draw the phasor sum of IC and this I here. So this is the new current I dash, and this is the new phase angle. Let it be phi 2. So this is I dash and this is phi 2. That is phi 2 is less than phi 1. So we have phi 2 less than phi 1. So that cos phi 2 will be greater than cos phi 1. That is, power factor of the load is improved. So the addition of the capacitor in parallel with the load improves the power factor. And here also we can note that the circuit current I dash after the power factor correction is less than the original circuit current I. And also we can conclude that the active component, that is the in phase component of the current, is I cos phi, that is I cos phi 1 or I dash cos phi 1, that is I dash cos phi 2 is equal, because while taking the active component or wattful component of the current, it is same in both the cases, that is before power factor correction and also after power factor correction. I cos phi 1 is equal to I dash cos phi 2, and also the lagging reactive component. So this is the reactive component. So first of all, the reactive component is this one, and after power factor correction it is this one. So the lagging reactive component is reduced after power factor improvement, and we can write as I dash sine phi 2. So after power factor correction, the reactive component is I dash sine phi 2, and which is equal to total reactive component, that is I sine phi 1 minus, this is equal to IC, that is IC. And as I cos phi 1 is equal to I dash cos phi 2, that is the active component, we can, if we multiply with the voltage, that is Vi cos phi 1 is equal to Vi dash cos phi 2. That is, the active power remains unchanged due to the power factor improvement. Also, if we multiply this one with the voltage, that is, we get V into I dash sine phi 2 is equal to V into I sine phi 1 minus V into IC. That is, net kVAR after power factor correction is equal to the lagging kVAR before power factor correction minus leading kVAR of equipment. So this is about the power factor improvement. So in the next class, we will discuss about the power factor improvement equipments. So thank you for watching the class. If you like the classes, please like, share and subscribe my channel.